Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 14, Organic Chemistry 2. We are still in chapter 3, Reactions of Aromatic Compounds. In the previous lectures, we covered Introduction to Electrophilic Aromatic Substitution, Activating Groups, Deactivating Groups, Determining the Directing Effects of substituent. Today we will talk about synthesis strategies. Recall from the previous lectures that having group on benzene affect the direction of the electrophile in the next step. We have ortho and para directors strongly activating like O-, NH2, NHR, NR2, and OH. Moderately activating group NHCOR, NHCOAR, OC double bond R, OC double bond AR, where R is alkyl and AR aromatic group. Weakly activating alkyl group, and alkyl group is stronger than aryl group. Finally, we have weakly deactivating the halogen family, fluorine, chlorine, bromine, iodine. These are ortho-para directors. When this group is electron withdrawing group, it directs the electrophile toward meta. Moderately deactivating carbonyl like aldehyde, ketones, carboxylic acid, ester, amide. Here we have sulfonates, nitrile. That's moderately deactivating. Very strongly activating quaternary nitrogen, NR3+, NO2, and CX3, where X fluorine or chlorine. These are deactivating. Let's examine our understanding on this topic. Consider the following monosubstituted aromatic ring. Determine whether the group on the aromatic ring is an activator or a deactivator. Then determine the strength of activation, deactivation, strong, moderate, or weak. Finally, determine the directing effect of the group. We have here phenyl group. On it we have heteroatom with lone pair. On this group we have C double bond N. The phenyl group is attached directly to a heteroatom with lone pair that delocalize into the ring, so it's activating, right? However, on this nitrogen, this lone pair is delocalized outside the phenyl ring, on the other way, toward the C double bond N. Because C double bond N, again, through bi-system electron withdrawing. Therefore, we predict that this group will be moderately activator, because it is a positive mesomeric effect. On the other hand, it is negative mesomeric. It's negative inductive effect with, again, a delocalization outside the phenyl ring. And since all moderate activators are ortho-para directors, then we expecting this group too to be also para directors. Okay? When there are two or more substituents on a ring, the directing group effects on both substituents must be taken into effect. Guideline 1. If both substituents have the same directing position, The effects reinforce each other, and usually one major product is formed. We have here methyl group and we have nitro. Nitro is meta directing, so it will be giving this way. CH3 is ortho para. Ortho is open, but para is blocked with nitro. Okay, so we have this position and that. They are on the same carbon, right? So reinforcing the electrofield Vr, and we get bromo in this on this carbon in 90% yield. It's 2 bromo, 4 nitro, toluene. If the directing effects oppose each other, we have here NHR CH3, that's also para, and this is a strong activating. We have here Cl also para, but T activator. So we have here ortho and para is blocked. For Cl we have ortho and para is blocked. So we are talking about either ortho in here or ortho in here. Here with activator and here with deactivator. Of course we will go with the activator. So we will get the brom in here 85%. Guide 3. In guide 3, if two positions are comparably activated, substitution occurs at the less hindered position. So we have here R CH3. We have here R tertiary butyl group, right? So it will be here ortho and para is blocked. And for the CH3, we have here ortho and para is blocked. We are talking about two ortho, here or that, and both are alkyl group, right? However, the tertiary is much more bulkier, a steric effect. Okay, let the reaction go on the ortho to the methyl group, forming, if we are making nitration, 2 nitro, 4 tertiary butyl toluene. To arrange the name right, it will be 4 tertiary butyl 2 nitro toluene. Guideline 4. The position between two other substituents is usually the last position to be substituted, again due to steric hindrance. We have here a methyl group. We have here a methyl group. So this is ortho para, and this one is ortho para. This position is strictly hindered, and the substitution here is last thing you think of. Okay, so we have it in here or in here, and since you have in this molecule symmetry, so both sides will be the same, and the product is 2 nitro 4 methyl toluene in 98% yield. Synthesis of disubstituted derivatives. When preparing disubstituted benzene derivatives, attention must be paid to the correct order of adding the substituent so that the directing group effects will give the desired product. We have here benzene, would like to transfer benzene to 2-bromoacetophenone. This acetyl group is meta-directing. Br is also directing. These two groups are meta to one another, 1,3, right? So the right way is to start with benzene, Friedrich-Crafts acylation reaction to give acetophenone. This group is meta-directing, so when you brominate with bromine iron 3 bromide, you will get meta-bromoacetophenone. the correct structure. If we start the other way around, start with benzene, then brominate. When you brominate, you get the bromobenzene. You acylate the bromobenzene with a steel chloride, aluminum chloride, then this is also para. So you get para, major and minor product also. No meta or traces of meta. So this is not the correct approach. In this example, we would like to start with benzene to get 3-nitroacetophenone. Here we have this group meta-directing, we have the nitro-meta-directing. Let's start with the Friedel-Crafts acylation to get acetophenone. This group is deactivating, meta-directing, so when you nitrate that nitric sulfuric mixture, you get the nitro in meta position. That's okay. Change the strategy. Start first by the nitration. You get the nitrobenzene. Nitro is very strong deactivating group. Very strong deactivating group. You react this with a steel chloride, aluminum chloride, no reaction. Devise synthesis of the following compounds starting from benzene, get us 1-chloro-3-ethyl benzene. The ethyl and the chloro 1,3, so they are meta to each other. The ethyl group is also directing group. The chloro also para-directing group, right? Well, they are meta. So the chlorine Cl here, we can't replace it by any other group. But this one, we can replace it by the acetyl group, meta-directing group. So we start with benzene, Friedel-Crafts acylation to give acetophenone. This group is meta-directing group. Chlorinate that to get the meta. Then we reduce this carbon C double bond O to CH2, and we get the desired compound. Benzene, Friedel-Crafts acylation, we get acetophenone. Chlorinate, we get this one, metachloroacetophenone. Reduce C double bond O to CH2 using zinc amalgam HCl. Clemmensen reduction, we get the target molecule. If we would like to start with benzene to get 4-nitrobenzoic acid, this group is meta-directing. This NO2 again meta-directing, but these two groups are para in this case. Well, we can still get that by first benzene, we put CH3 instead of COOH, and later on we can oxidize the CH3 to COOH, to carboxylic acid. So Friedel-Crafts alkylation to toluene, then nitrate, we get that, para and ortho, we can isolate, okay, and then we oxidize the benzylic carbon with chromic acid to form benzoic, right? First step, CH3Cl aluminum chloride, toluene, nitrate, nitric sulfuric, get us para-nitrotoluene, chromic acid oxidation with potassium dichromate sulfuric acid mixture to get this carbon COH. This is a desired molecule. Well, I would like to transfer tertiary butylbenzene to 1-tertiary butyl 2-nitrobenzene. This group is already ortho-para. If we nitrate, we get ortho and para, and since this is a very bulky group, then we will get major para, and the target molecule will get trace. To force the reaction to go ortho, we have to block the para. So the first step will be sulfonation. We blocked here. Then we nitrate using nitric sulfuric for this group, ortho, for this group, meta. They are following the guideline 1 in the same direction, so we get nitro in this position, right? We know that SO3H, the sulfonation reaction, is a reversible reaction. So taking this molecule in water, sulfuric acid, and heat, you reverse, you desulfonate, and you get the desired molecule. For each of the following compounds can be made with Friedel-Crafts acylation. Identify the acyl chloride and the aromatic compound you would use to produce each compound. For the first one, NO2 is strongly deactivating, meta-directing. On the other side, methoxy is strong activating also and para-directing. Cutting in here using anisole and meta-nitro acyl chloride will work. On the other hand, cutting in this side nitro and acyl nitrobenzene and acyl, this acyl chloride, it will not work because nitro is very strong deactivating group, and the acyl group is using acyl chloride and aluminum chloride, so it will not work. There is no reaction. For this compound, we have here two groups. Methoxy, and it's also para, strong, and here the acyl is here meta to OCH3, and we have here tertiary butyl that's weak activating ortho para, and the acyl group is in the para position to this group. Okay. For this one here we have a methoxy, and we have here the acyl para to it, and it's also para directing group. Well, if we cut in here, we start with anisole, and this acyl chloride, the reaction will go. If we cut the other way around here in this one, now this group will be also para, but it's not in control. The methoxy is a strong activating, it will be in control, so it will be, this is a para position to it, and this is a ortho position to it. Okay, so we need the connection in here. No, it's not going to be in here. The reaction will not go this way, and the reaction will go this way. That's not the desired molecule. See you next lecture.